Hello, everyone. My name is Elizabeth Hughes, and I am a sales engineer for the Mobility House who sells a charging energy management system called ChargePilot. ChargePilot is an automated load management capable charge management system, and today I'm going to be covering the basics of what is automated load management, what problems does it solve, what do you have to do in order to use it, and then also how automated load management affects site design. But first, I want to set the stage on why automated load management is so important in the first place. As you probably know, we're experiencing a shift towards the electrification of transportation. And as we go through that shift, fleets are going to use more and more power. However, this shift coincides with unprecedented supply chain shortages in the same type of grid equipment that is going to be needed to allow these sites to have more and more power. The stark reality of it is, though, that an unexpected grid upgrade can cost you more than a year in project lead time delays, according to the Center for Sustainable Energy. And if you have to pay for a grid upgrade, it can cost over $500,000. On the blue side of my screen here, I have an example site that I will be using throughout the rest of the presentation to cover various concepts regarding ALM. Now, for our example site, our customer wants to install 4 150 kW rated chargers on a 500 kW rated connection. Now, for those electrical engineers in the audience, I have assumed a power factor of 1, and for those non-electrical engineers in the audience, I have done the math for us. So those 4 150 kW chargers are going to give us approximately 600 kW of new load added to the site, while our 500 kW connection is going to have to be derated by 80% to 400 kW because EV chargers are considered continuous load inside the NEC. And here we can see the problem really easily in that we only have 400 kW of space for load while we want to put on 600 kW of new charger load. Now, if we wanted to do this site without ALM, we would have 3 alternatives. Each of the alternatives has its own various degrees of added project expense, delay, or downsizing, or in some way is suboptimal. The first is we could wait and pay for that grid upgrade, but of course, because distribution equipment is commoditized, there is a linear relationship between the size of the grid equipment needed and its cost and generally the time it takes to manufacture. So as our grid upgrades grow larger and larger, they're going to cost more and more, and the equipment is going to take longer and longer to produce, causing more and more lead time. The second option that we have is we can install fewer chargers on the site. Now, the next question you may have is, well, how many chargers? So we need to make sure that the total nameplate capacity of all of the chargers combined is less than the existing power of the rated connection. So in our example site's case, that's going to be 2 chargers, as 2 times 150 kW gives us 300 kW, which is less than that 400 kW of space that we have. Now, of course, installing half the amount of chargers is going to affect our customers' operations, possibly requiring them to hire someone to physically move around the vehicles, or they may not be able to run those vehicles at the duty cycle that they were originally planning. The final alternative they have is they could always derate the chargers. Derating is when you use software to set a fixed max cap of power that the chargers are going to be able to use. Now, this has a couple different disadvantages, which really come from the idea that generally how derating is applied is you'll take your full 400 or whatever the space on your connection is, and you'll divide that out by the number of chargers you have on the site. So for our example site, that'll be 400 divided by 4 chargers, giving us a software cap of 100 for each charger. Now, that is suboptimal because obviously you're paying for chargers that are able to do that full 150 kW. So you're obviously paying more money for chargers that are going to be limited. The second way that's suboptimal is that it really doesn't take into account any site dynamic changing variables, such as like the need to prioritize one vehicle over the other. And finally, the only time all available power is used is if all of the chargers are plugged in on site. For example, looking at my little graph here, if you only have 3 chargers plugged in, only 300 kW of power is ever going to be used at max, meaning we are losing 25% of the site's available power, which is very bad considering this site already had power constraints. Now, I've talked a lot about what problems ALM solves, and I've also talked about some of its alternatives, but now I want to talk about what it actually is. So automated load management is the use of technology to control charger loads such that those charger loads stay below a safe limit. Now, because we're keeping that charging load below a safe limit, we are able to install more charger nameplate capacity than what would normally be allowed on that grid connection. And because we keep the charger load below that safe limit, we are able to avoid, reduce, or prolong the need for grid upgrades. When we think about avoiding grid upgrades, maybe you're really close to that cap, right? So maybe you only need, 20% more power under normal calculations, and then your site could avoid a grid upgrade entirely. But with ALM, you can just, completely shift around that power a little bit and not have to trigger that grid upgrade. When we think about reducing grid upgrades, maybe you were originally going to need a 1 megawatt connection, and now with ALM, you're only going to need a 0.5 megawatt connection. With going back to talking about that linearity in relation between the size of equipment and its cost, that's going to roughly translate to a 50% cost reduction. And of course, we can think about prolonging grid upgrades with ALM. Many fleets electrify in phases. For example, you could have a fleet that's eventually going to be 100 vehicles large, and they're going to do it in 4 phases every 2 years. Well, that first 25 vehicles generally will trigger a grid upgrade, but instead with ALM, what you could do is use ALM to handle the load on the site with the first 25, and then talk with your utility and aim to get a transformer or other grid equipment such that your site will eventually be sized to that full 100 vehicles, but you don't have to do it immediately when those first 25 vehicles go in the ground. You can, use the time in between that first phase and that second phase to really, give your utility some time to work with. And you're allowed to do all these things if you do 3 things. The first category is you need to talk to all of the parties involved. You got to talk to your authority having jurisdiction, make sure it's allowed in the National Electrical Code in your area. More on that later. You got to talk to your electrical contractor as they need to factor in automated load management into their site designs. And you also got to let the utility know that you're planning on using automated load management for your specific site. The second is you need to run simulations to see how automated load management might affect your fleet's operations. While automated load management can help in a variety of cases, it's not a magic bullet. It can't make more power appear. And so if your fleet needs to always be charging at 100% its power throughout the entirety of the day, then probably ALM is not going to be the right solution for you, and you're going to actually have to do that full grid upgrade. And finally, from a technical perspective, we need to make sure that the EMS set point, that safe limit I mentioned earlier, is set to the right number. Now, to think about that more, on our example site, we had 400 kW left on our connection, so that is what's going to be our EMS set point. Generally, it's going to be the space on the connection or lower. And because we're using a ALM-capable charge management system like Charge Pilot here, we are allowed to install all of our chargers and not trigger any site upgrades. Over on the white side of my screen, I have a graph here so that you can see the differences between automated load management and derating. So with automated load management, power is shared between the chargers, even when not all the chargers in use. Right here, I have the same situation as before, where only 3 chargers are being used. But you can see in this scenario, charger number 1 and charger number 2 are using their full nameplate capacity of 150 kW, where charger number 3 is using the rest of the 400 using 100 kW. Now, I've briefly mentioned equipment rating earlier in this presentation, but generally equipment is sized using this formula. So usually you'll sum up the max loads on your circuit and then you will apply a safety factor. This safety factor is related to how the grid equipment is rated. So some grid equipment is rated 80% for continuous loads and some grid equipment is rated to 100% for continuous loads. If your grid equipment is rated to 80%, you're going to need to apply this 125% safety factor. And if it's rated to 100%, then you will just be multiplying by 100% here. A really good example of this is, some circuit breakers are thermomagnetic circuit breakers and generally are rated to 80%. And finally, of course, multiplying these two variables together, we get the equipment size. How ALM changes this equation is that for the variables in blue, we're going to swap out the max load for that EMS set point. And since that EMS set point is a lower number, of course, we are going to eventually have an equipment size reduction, which will also, of course, lead to our cost reduction. Now, I also mentioned the National Electrical Code earlier in this presentation. The National Electrical Code is the set of rules that govern the design, installation, and operation of electrical equipment in the United States. And it's a very extensive set of rules, and it covers many things, including circuit protection, electrical connection types, and in ALM's case, equipment rating. Now, a new version comes out every 3 years, and the states then have the choice of when they want to go about adopting the new version. This means we have a patchwork of different NEC versions across the United States. For example, we have Oregon that just adopted NEC 2023. We have New York State that is using NEC 2017, and we even have Kansas that is using NEC 2008. Now, this matters because ALM is first allowed in the National Electrical Code in 2014, and it's called ALM from 2014 through the 2020 NEC version. In 2023, the terminology shifts from automated load management to the same type of technology being called an energy management system. There may be other rules that allow the use of automated load management on one of your sites, so it's important to contact your local authority having jurisdiction along with your local utility. The Mobility House has done automated load management across the country in various states, but the site I want to talk about today is Long Beach Transit, a site in California, where we are powering a transit fleet using 10 chargers to charge 20 buses using automated load management. And because we're using automated load management, the fleet was able to install 1.8 megawatts worth of charger nameplate capacity on only 1.1 megawatts of available connection capacity. So bringing it all together, I really want you to remember 4 things. Automated load management regulates the amount of power below a safe limit. It helps install EV sites by avoiding, reducing, or prolonging the need for grid upgrades. It affects the sizing of the equipment needed and therefore affects permitting. And finally, you need to remember to talk to your authority having jurisdiction, your electrical contractor, utility, and of course, your charge management provider ahead of time. Thank you so much.